Good evening, students. Am I audible?
Yes, sir.
So, what was the last topic we were discussing? I think we came to the concept of torque, right? Right, we have seen motion of center of mass in the previous class. I think we are done with it. So the next concept that we are supposed to see is called as torque. Please write it down. Or it is also called as moment of force. Okay. So torque is basically represented with the symbol tau. Here, guys. Right. So write it down. Torque can also be called as rotational force. Okay. So it is defined something like this. So whenever I ask you a question, what is responsible for the translatory motion of an object? What will your answer be? So if you put a question like, what is responsible for the translatory motion of an object? What is your answer? Is it not force? Similarly, if an object has to rotate, then we need to apply torque across it. Okay. So how is torque defined as? Torque is defined as the force into perpendicular distance. Okay. So force applied multiplied with the perpendicular distance is what we call it as torque. Guys, am I clear? Am I audible?
Yes, sir.
Okay. Now, let me show you something. Suppose, see, let me take this mic, okay? I have this mic as an example. I hope you guys are able to see that. Now see, if I try to move it like this, am I not rotating it? I hope you guys understood what is the meaning of rotation, right? So is it not rotating? So where I'm applying the force at this point, when the force is applied, the object starts revolving. Correct? That is called as rotation. So this force and this distance is there, right? So if you observe, it is rotating about this axis. Right? Am I clear? So it is rotating about an axis passing through this point. The axis is like this. Okay. So when it is rotating, this force that you apply multiplied with this perpendicular distance from the axis of rotation is what we call it as torque. Am I clear?
Yes, sir.
Yes. Okay. So that is the basic definition of torque in terms of scalar quantity. But sometimes you will have to use it in the vector form because torque has a rotation associated with it. We call it as clockwise moment and anti-clockwise moment. Let me explain what it means. Okay. See, if you take the axis of rotation, from the axis of rotation, let's say I'm applying a force at this point. See, I'll try to do different experiments and see, I'm applying a force at this point, it is rotating. Okay. If I try to apply force here, it is rotating, but what is happening? I personally feel a lot of pressure here. Guys, you are able to understand what do I mean by pressure? I meant to say that I need to apply a lot of force to make it rotate at least to this extent. Whereas here, I apply little force also, it is able to rotate fast. Look at the speed with which I'm trying to rotate. right? If I apply it here, similar, if I apply here, it is really tough. I'm not able to rotate. Okay. Are you guys able to understand what I'm trying to say? So, what are the important parameters on which you can generate more amount of torque? What do you think are more appropriate things? One is the distance. Distance from where? Distance from the axis of rotation to whom? Axis of rotation, the point where you're forcing. Let's take the example of your door. Okay. So where is the handle of the door? The handle of the door is always at one of the edges, right? Had it been at the center, do you think it would have been easy for you to rotate?
No.
Guys, I need some interaction. It would have been slightly difficult, right? Purely, it all depends on how much is the distance you're trying to apply between the axis and the point of. Based on that, torque is also defined something like this. So based on that, the torque is defined something like this. Torque is r vector cross f vector, where r is the distance. Here I'm not talking about perpendicular distance. Distance from axis of rotation to the point of application of force. And this F vector stands for force. Okay, please write it down. R vector cross F vector is the mathematical expression for torque. Okay, it is not F vector cross R, it is R vector cross F. And it is also defined as RF sine theta times n cap, where n cap is a unit vector perpendicular to both whom? R vector and F vector. Is it clear? So if I take this to be the axis of rotation, and if I take this to be the point of application of force, and if this is R, okay, let me say this is F vector, then the angle between them is measured like this. Okay. Then if force is like this, then force into perpendicular distance is what is going to be r sine theta. Okay, this r sine theta, if I combine and write it, then I can write it. So torque in terms of magnitude can be written as rf sine theta, where r sine theta is nothing but the perpendicular distance. So I can write it as r perpendicular into f. So please make a note of this. So how do you mathematically define torque? Torque is r vector cross f vector, or it can be written as rf sine theta times n cap. Okay. So I hope you have written it. Next is finding the direction of resultant. Okay. So if I have a vector like this, C vector is equal to cross B vector. If I have something like this, then how do you find the direction of A vector cross B vector using the right hand thumb rule? Guys, how do you find Okay. If I have A vector cross B vector, okay. If I have
Sir,
A
if it
vector
is,
cross B vector, then yeah, please continue, Raghav. Yeah.
it would come towards us. If it was if it was B vector into A vector, it would go out of the page.
Okay. Let me see. So this is A vector, and I'm seeing from your end. This is A vector, this is B vector. So when I say A vector cross B vector, from A vector, you need to curl the fingers of your right hand towards B vector in the shortest direction possible. Correct? So from that is, keep B vector fixed, keep the second vector fixed, rotate the first vector towards the second vector. When you rotate it, you're able to see from there, right? In which direction am I rotating this pencil? Clockwise or anti-clockwise? Guys, you're able to see, no? Am I rotating this clockwise or anti-clockwise?
Anti-clockwise.
Right, anti-clockwise. No, means it says you need to take your right hand and curl the fingers of your right hand in the anti-clockwise direction and extend the thumb. The thumb goes in the outward direction. So in this scenario, right, in this scenario that I've shown, from A vector towards B vector, you need to curl your hands in the anti-clockwise direction. So what is the direction of resultant? It is in the direction of K cap, that is out of the plane. Okay, and this is called as anti-clockwise rotation. Accepted. Similarly, if I do B vector cross A vector, what would have happened? Clockwise rotation. So clockwise rotation will be into the plane.
Cross.
Yes, it will be into the plane. So you are able to do it on your book, right? Do it on your book and see. Draw B vector and A vector. Curl the fingers of your right hand on the book. Are you able to see that your thumb is pointing towards the book? Yes or no?
Yes, sir.
Right. So this is the reason why the same logic we do R vector cross F vector, right? So to find the direction of resultant, we know that torque vector is equal to R vector cross F vector. So if R vector is like this and F vector is like this, okay. For finding the torque, you need to do R vector cross F vector. In this case, you are supposed to curl the fingers of your right hand in anti-clockwise direction. So this is also called as anti-clockwise moment. And remember, anti-clockwise moments are always positive. Please make a note of it. Anti-clockwise moments are always positive. Why? Because they face towards you. The thumb faces towards you. Similarly, clockwise moments are negative. Am I clear?
Sir,
Tell me.
sir, in torque, can we say that the force is always perpendicular to the distance?
Need not be. Need not be. Need not be that the force is always perpendicular. It can be in any direction.
Okay, sir.
That is why theta is coming into picture. We wrote R of sine theta, right? Where theta is the angle between the R vector and F vector. Okay. So let's do a problem to understand how it works. I hope you guys made a note of this. Anti-clockwise moments are positive. Clockwise moments are negative. Okay. Suppose r vector is given like this: I cap minus j cap plus k cap, and f vector is equal to I cap minus j, I cap plus j cap minus k cap. Okay. Find torque. So how to do this problem? R vector cross f vector. You guys remember this method? It's called as determinant method. I cap, j cap, and k cap. What should I write at the bottom? 1 minus 1 1 1 1 minus 1. So it will be I cap into, what should I write? 1 minus 1 minus j cap into minus 1 minus 1 plus k cap into 1 plus 1. This will be 0. This will be 2 times j cap plus 2 times k cap. So this is going to be the value of torque. So you would understand the importance in the task is what is going to be the SI unit of it. The SI unit of
Newton meter.
yes, that's right. So we saw Newton meter somewhere else also. What is it? We saw Newton
Work
meter
done.
somewhere else also. Force into displacement, work done. So where work done is, where in the case of work done, Newton into meter is called as joule. In the case of torque, you don't write it as joule because joule is a measure of work. You don't say that the torque is these many joules. Okay, so here with respect to torque, you should leave it as Newton meter. Don't write it as joule. Please make a note of that point. Clear? Let's go to the text. The next concept that I need to introduce is moment of inertia. Okay. So write it down. What is moment of inertia? So moment of inertia is basically defined. Okay, I'll come to that point. So first of all, you guys tell me what is inertia? What is inertia? It is a tendency of an object to resist force. Means if an object is moving, if an object is at rest, then it will resist the force that is trying to move the object. If the object is already in uniform motion, it will try to resist the force that is trying to stop it. Right? That is inertia. Right? Now, what is moment of inertia? Okay, guys, guess it. I told you, right? Wherever you have rotational motion, you use the word moment. See, for example, the previous topic was moment of force. Means it was rotational force. Similarly, what do you think is moment of inertia? Guys, unless you understand the significance, this chapter is very tough. You should at least try. I'm not sure if you guys are there on the other end. So I already gave you the hint. Moment of force means torque. That is rotational force. Then what is moment of inertia?
So rotational inertia.
That's it. It is rotational inertia. So you already know what is the definition of rotational inertia. So if there is an object which is opposing the torque, okay. So listen to this question. If there is an object which is resisting the torque applied to it, what will torque do? Torque will put to the object in rotation motion. So if there is an object which resists the torque applied to it, then that object is said to have rotational inertia or moment of inertia. Means the resistance offered by an object to the torque applied on it is what we call it as moment of inertia. Okay. Now, in the case of translatory motion, what is the measure of inertia? Inertia is measured by, in the case of translatory motion, how did we measure inertia?
Mass.
Or inertia, we didn't actually measure, sorry,
Mass.
completed? That's right. So more is the mass of the object, more will be the inertia. Similarly, in the case of rotational inertia, there is nothing like mass or something. I'll come to that point. So in the case of translatory motion, we concluded that if the object has more mass, then it has more inertia. Correct? Is there any mathematical expression for inertia in the case of translatory motion?
No, sir.
So mathematical expression is nil, no expression. Whereas in the case of rotational inertia, what will happen? There is a mathematical expression. So what is that mathematical expression? Let's see what it is. So if I take this as the axis of rotation, okay, and let's say there is a mass. There is a mass which is a point mass actually, okay. There is a point mass which is present at a distance r from the axis of rotation. Then moment of inertia is defined like this: mass into square of perpendicular distance. Remember, the distance between a point and a line is always perpendicular distance. So this will be m into r square. Okay. So the moment of inertia is mass into distance square. The SI unit here will be kilogram and distance square is meter square. So kilogram meter square is what we call it as moment of inertia, and this formula mr square is applicable only for point mass. By now, I hope you guys are clear with what is point mass and what is extended mass. Am I right? Okay. Now listen to this carefully. For n particle system, there are different masses present like this. Okay. Then the moment of inertia of each particle is going to be something like this: m1 r1 square I2. You guys tell me. m2 r2 square I3 will be m3 r3 square. So on till what will be the moment of inertia of nth particle? It will be mn
Mn
rn square.
square.
Remember, that's right. So remember, all these are scalar quantities. Okay, all these are scalar quantities. Then the total moment of inertia will be equal to I1 plus I2 plus I3 plus so on plus In, which is called as M1 R1 square plus M2 R2 square plus so on till Mn Rn square. Okay, this is the total moment of inertia. So if I have to give a general formula for it, it is sigma mi ri square, where I is equal to 1 to n. Okay, so this is how you calculate the moment of inertia for a system of n particles. Okay, now comes an important question, but it is not in real time. If you see the pen you are holding, the book on which you are writing, all these, see for example, you take your book. So if you take your book, what is happening? I'll come to that. So if you take your book example, it is like this, okay. Let's say the book is like this. You want to write in a particular page. What do? You open it like this, right? So the book is rotating about which axis? So you are able to see an axis here, right? At the joint, right? One page is revolving with respect to another. Again, you turn another page, it will turn like this. Am I right? Are you have to understand what I'm trying to say? But all these are extended objects,
Yes.
right? So do these objects also have moment of inertia associated with them? What do you think is the answer? For example, the door, it is revolving. Similarly, the mic which I showed you, that is revolving. All these objects are extended objects. They are not points. Maybe they are made up of multiple points, right? They are made up of multiple points. That is a different story. But as a whole, it is an extended object. It has a finite size and a shape associated with it. So can I call this like I need to think of an important point. I told you moment of inertia. The formula is m into r square only for point object. Is there a possibility for it to exist for an extended object also? What do you think is the answer?
Yes, sir.
The answer is yes. Yes, it does. But the question is, how will you find it? Okay. So let me see how much logic you guys are applying for extended objects. Okay. I'm not going to directly reveal the formula. I'm going to make you think. For that, the logic I'm going to use is I'll revisit the concept of center of mass. For point-sized object, the x-coordinate of center of mass is sigma mi ri, the whole divided by sigma mi, where I is equal to 1 to n, I is equal to 1 to n. And for finite size, what did I say is the answer? X-coordinate of center of mass is equal to, tell me. Recollect. No, I told you, no, there is a method to remember. I showed you a derivation also. Integral something. 1 by capital M into integral of, what should I write?
XDM.
Integral of, so what did we do? Sigma mi is replaced with capital M. Sigma is replaced with integral. In the place of Ri, I replaced it with X. In the place of M, I replaced it with dm. Okay. In a similar way, What do you think we are supposed to do here? Can you try it out? Try, no. So sigma is there. Generally, sigma is for discrete objects. When it comes to continuous system or extended objects in physics, what are we supposed to do? Replace sigma with
Integral.
integral. Mi. In the place of mi, what should I replace with? Dm.
Derivative.
In the place of, yes, in the place of Ri square, I need to replace it with R square. So to be more precise, integral of R square dm is what is going to be the moment of inertia of extended objects. Is that clear? So you need to take a proper limits into consideration, but that I'll tell you how to do it. Don't worry about it. Okay, I'll show you one derivation alone. Try to understand this. So moment of inertia of a thin rod of mass capital M about its center of mass. Okay, so there is a thin rod. Thin rod in the sense its thickness is ignored, and this thin rod is revolving about whom? About the center of mass. So center of mass of a thin rod is generally about its center. Right? Am I clear to this point? Let's say the length of this rod is capital L and its mass is capital M. So first question that we need to ask ourselves is this a point object or an extended object? Guys, tell me, is this a point object or an extended object? I asked everything. Extended. Okay. So when it is going to be extended, what did we do in the case of center of mass? Revisit your notes and tell me. So in the case of center of mass, we define something called as mass density. So here, since it is a thin rod, rod is one-dimensional. What is the type of mass?
Linear.
So lambda is equal to m divided by L. Correct? Then from the axis of rotation at a distance r, where because r is a variable. Okay. Take element of thickness and dm. Consider mass dm of this dm. Okay. Then how is dm defined as? I told you dm divided by dr is equal to capital M divided by L. Why is it so? Because when I told you it is uniform, then the amount of mass distributed over a unit length is always a constant. So dm by dr is equal to m by L. Then dm will be equal to m by L into dr. Accepted? Little bit of mathematical expressions. Is that clear? So let this be equation number 1. So what is the moment of inertia of this rod? Integral of r square, where r is this value, r square into dm. So integral of r square is r square only. What is dm? It is m divided by L into dr. Okay. So what will come out of the integral? M by L will come out, integral of r square dr. Now tell me, where does R vary from? Since R is at the center of the rod, if I take that center as origin, this will be minus L by 2 and this will be plus L by 2. Correct? Now tell me guys, it is M divided by L into integral of R square dr. What is the answer?
R cube by 3.
Very good. So it will be M by 3L into L cube by 8 plus L cube by 8. The reason I wrote plus L cube by 8 is because you will get minus of minus L by 2 the whole cube divided by, sorry. Okay, wow.
Sir, it should be L cube by 24, right?
I took this 3 out now. So it should be 2L cube by 8 or ML cube divided by, sorry, ML square divided by 12. So the moment of inertia of a thin rod when it is revolving about its center is M into L square by 12. First, let me explain the significance of it and visualize it. Then you can make a note of the formula. 1 minute. So if I take this as the thin rod, then for this thin rod, the axis of rotation is going to be at the center. So if this is revolving like this, right, are you able to visualize? If it is revolving like this, where it has a mass M and length L, then the moment of inertia offered by this rod about its center of mass is M into L square divided by 12. Is that clear? Is that clear, guys?
So can you repeat
Sir,
it?
could you repeat once?
See, if the rod is revolving about its center of mass like this, where its mass is M and length is L, then the moment of inertia of this rod about this axis of rotation is ml square by 12. Now you can ask me a question. So, is the axis of rotation confined only to center of mass? No. I can make this whole object revolve like this also. Means I can fix one of the ends as the axis and make it revolve like this.
Sir, so it doesn't matter where the force is applied.
The important point is moment of inertia will change depending on where the axis of rotation is. That was the next question I was supposed to ask. Okay, I just told you that it can be revolved about any axis. If you see the current derivation that we did, what did we do? We derived the moment of inertia of a thin rod about its center of mass. Okay, for which the answer is ml square by 12. First, make a note of it, then I'll go to the next step. Done? Shall I go to the next one?
Yes, sir.
So what is the moment of inertia of the same rod when this is the axis of rotation, when it is rotated about one of its ends? So question is moment of inertia of thin rod about an axis at one of its ends. How do we rotate it? Like, how do we calculate? From the axis of rotation, what are we supposed to do? Consider a distance r, and after a distance r, see, this is the technique for any integration, guys. If you understand this, you need not worry about integration. Understand it again, always from the reference point. In this case, who's the reference point? One of the ends. So from one of the ends at a distance r, if you take a thickness dr, okay, there will be small mass dm that we'll consider. So what is dm again? dm divided by dr is equal to capital M divided by L. So dm will be equal to M by L into dr. Right? So what is the moment of inertia formula? Integral of r square dm. So integral of r square into dm is M by L into dr. See, if you're well versed, right, you can directly use this step. Now tell me the range of r, guys. Always take the axis of rotation as origin. Tell me. So where does r vary from? R varies from 0 to capital L. So M by L into R square dr between 0 to L implies M by L into R square dr is how much? It is L cube divided by 3 between 0 to L. So when you apply the upper limit and lower limit, ml cube by 3L is going to be the moment of inertia. If this and this gets cancelled, it will be m into L square divided by 3. So this is the moment of inertia about one of its ends. Okay, means the same rod, depending on where you choose the axis of rotation, the moment of inertia value is changing. Now tell me, out of the two values ml square by 12 and ml square by 3, which one is more? Guys, I asked a simple mathematical question. Out of ml square by 3 and ml square by 12, which is more value?
ml square by 3.
ml square by. This is more value. Means, what did I say? Now we will understand the significance. ml square by 3 is greater than ml square by 12. Now listen to this carefully, guys. What do you understand? So I told you that moment of inertia is the resistance offered by an object to whom? To the torque applied. So moment of inertia is the resistance offered by an object to the torque applied. Correct? Now, if you rotate the object, if you rotate a thin rod about one of its ends, there the moment of inertia will be more, means the resistance offered will be more compared to the place where you, compared to the axis of rotation being taken at the center. Am I clear with this? Am I clear? So, you have to note an important point. The moment of inertia of any object you take will be the least about its center of mass. Please make a note of it. Moment of inertia of any object you take will be the least about whom? Will be the least about the axis considered through the center of mass. Any other axis, the moment of inertia will be more because of the uneven distribution of mass. Because of the uneven distribution of mass. Someone is asking a question. What is it?
Yes, sir. Sir, you said the moment of inertia, if the axis is at the end, then it's a maximum. So, but the torque is maximum at the ends, right? It's minimum in near to the center or the axis of rotation. Torque, sir.
See, torque is different, no? See, the meaning is more is the moment of inertia, more is the amount of torque that we need to apply. Why it is so, you'll understand maybe in 5 to 10 minutes. I'll come to that point. So as of now, I wanted to stress on the point that moment of inertia will be the least through the axis of rotation considered through center of mass, and maximum when it is considered at any other point. I'll not say maximum, it is more compared to any other point. Generally, it will be maximum at the end. Tell me.
So no, sir. What I meant was,
Yeah,
suppose we consider the axis of rotation as one of the
Your voice is breaking after that.
Sir, can you hear me now?
Yeah, but there is a lot of disturbance. There is a lot of disturbance. I don't know. Is it only for me, or you guys are also, others are also able to hear?
His voice isn't clear, sir.
His voice is breaking, no? Is my voice breaking or his voice? I just want a clarification.
So his voice is breaking, and sometimes, like before, your voice was breaking too.
Okay. See, my voice breaks. No, please stop me. Or else you guys might miss some important points. So one of the, I didn't understand, Subrajit, you didn't complete it. I'm still in suspense with this word. One of the.
Sir, can you hear me now?
Yeah, it is better. Yeah.
Yes, sir. Sir, my question was, suppose the axis of rotation is one of the ends of the rod, and the moment of inertia is maximum at the other end.
It's same. Moment of inertia about any of the ends is same because both the ends are identical. See, you don't try to. If you see the term that moment of inertia is maximum, that means you need to apply more amount of torque to put that object into rotation about that axis. That is the meaning of it. Okay. So if I say the moment of inertia of an object, see, if I say the mass of an object is more, you need to apply more amount of force to make that object move. In a similar way, if I say more is the moment of inertia of an object about a particular axis, more is the torque you need to apply to put that object into rotation. That is what I meant.
No, sir. Actually, I'm asking a different question.
Please tell me, what is it?
Yes, sir. My question is, suppose. At one of the ends of the rod. So if we apply the torque in the other end, then it should face maximum moment of inertia, right? Because the axis of rotation is at one end. Whereas if the axis of rotation was in the middle, then the distance between the applied torque and the axis of rotation becomes less. So the torque is less basically.
Okay. See,
so but the moment of inertia.
I understand. See, but I will suggest you only one thing. Okay, you're thinking more in terms of mathematics. I would suggest you to think in terms of more of practical application. What you asked is 100% right. I'm not denying it. It is 100% right. Yes, torque is more when you keep it at the end because you are thinking in terms of the distance from the axis of rotation to the point of application of force. You think of the same thing in reverse. What I'm trying to say is, if the object is hinged, okay, if I give you a rod and if you hinge the top, you know what is the meaning of hinge, right? Like how the doors have hinges. If the rod is hinged at one of the ends, then if you want to apply torque at this position, yes, you need to apply more amount of torque. Okay, that is more appropriate. But what you told is torque will be more. Torque will be more means like you're saying as if more amount of torque is produced. No, we need to apply more amount of torque to put this object into rotation. Okay, both are same, but I'm just giving you a more appropriate perspective. That's it. I hope you understood what I'm trying to say. Right?
Yes, sir.
Right. So always I want you guys to think in this way. See, moment of inertia is more means torque will be more. Don't think like that. Moment of inertia is more. We need to do something more. What is it? We need to apply more amount of torque to put that object into rotation. That is the meaning. Okay. So that is the thing. Similarly, if it is hinged at the center, then what would have happened? Then you need to apply lesser amount of torque to make it rotate. Okay. Now, one last point is relation between torque and moment of inertia. So torque is equal to F into R. Correct? What is F? It is M into A into R. Similarly, what is moment of inertia? M into R square. Okay. I'm doing this derivation on a higher level. Okay. So torque divided by R will be M into A into R divided by MR square. M and M will get cancelled. R and R will get cancelled. A divided by R. Can you guys tell me what is A by R equal to? You remember this formula, A is equal to R alpha. So alpha will be equal to A divided by R. So torque will be equal to I into alpha. So Prajit, I hope you will get better clarity now. They both are directly proportional.
Sir, I have a doubt.
Is that clear? Please tell me.
Sir, suppose we don't consider the case of moment of inertia. We only consider torque. Suppose here. So if we apply torque at the end, like far away, so like the distance is more between the axis of rotation and the application of force, then less torque needs to be applied to move the object. Whereas if we apply the force close to the axis of rotation, then more torque force needs to be applied.
Yes, more torque, more force needs to be applied so that the torque is maximum.
Yes, sir. So, but in the case of moment of inertia, it's the opposite, right? Like the more, suppose the axis of rotation is at one end, then like the torque, like the moment of inertia is more. Whereas if we don't consider the moment of inertia, torque needs to be applied less, right?
No. You are getting confused. See, when it is revolving like this, right? Its moment of inertia is ml square by 3. The meaning of it is, see, at this point, if you apply force, this force multiplied with this perpendicular distance is called as torque. Okay. So, since the distance is more, understand, since the distance is more, you apply lesser amount of force also, you will be able to generate more amount of torque. Because force into perpendicular, lesser force, more distance. So that the product of both is balanced and you will be able to generate more amount of torque. Okay. You're able to understand what I'm trying to say?
Yes, sir. Sir, can you just explain the same thing with the axis of rotation at the middle?
Okay. Axis of rotation at the middle, same thing. You see, if you apply force at this point, force into, there is some perpendicular distance. Let me call this as x. Okay. See, the reason why generally the door handles or anything is hinged at the end is because you apply lesser force, you can rotate it faster. Whereas when it is at the center, you need to struggle with it. That is the basic idea behind the design of a door.
Sir, but at the same time, if it's in the center, the moment of inertia is less. But if it's at the end, then the moment of inertia.
Okay. Okay. See, you need not worry about that. No moment. See, I told you the significance of it. You're literally taking the meaning of it. You know what I'm trying to say is moment of inertia is the least Okay, let me make you experience it. Okay. Let me make you I want you all to do this activity. So you have a pen in your hand, right? Yeah. Rotate it like this. Rotate. Is this easy or rotating it this? Which one is more easy? Is this easier or is this easier? Try and see. No?
Sir, if we rotate from the center.
Right. That is the meaning of moment of inertia being more. When you fix this as rotation, from the axis of rotation, there is more mass distributed on one side. That is the reason why we need. So what I'm trying to say is moment of inertia is this object is putting you into a struggle of making it rotate. When you're trying to rotate it up about one of the ends, maybe you try it here, it will be comparatively easy, but not as easy as how it was at the center. You're able to understand what I'm trying to say. So generally, with respect to the axis of rotation, if more amount of mass is distributed on one of the sides, it is difficult to put that object into rotation. That is the significance of moment of inertia. Okay, don't get confused between both. You'll slowly understand because this takes some time. All these are practical applications. I'll slowly go into it. You're able to understand, guys. So as of now, have this point,
yes,
because many people fail to understand it. They look at it like a formula. See, that is the reason why this chapter is actually it's a nightmare for many people. I'm telling you. You go and ask your friends, they will tell you. This chapter is literally tough for people who don't understand the basics. So what I'm trying to say, more is the mass distributed on either of the sides with respect to the axis of rotation. That is why I'm stressing on that point. With respect to the axis of rotation, then more will be the moment of inertia, means more tough it is to put that object into rotation. Okay. So that is why I told you need to take a lot of effort. Effort in the sense you need to apply a lot of torque. That is what I meant by torque. So I didn't mean it was, I didn't take the R vector, F vector into consider. I didn't go into the mathematical meaning at all. I'm just saying that object you cannot rotate it comfortably. That is the significance of moment of inertia. Okay. The reason why I'm stressing this much on this point is because you have assertion reason. At that point, you should not get confused. You should be in a position to answer it comfortably by visualizing and having a feel towards it. Clear? You think about it, guys. By tomorrow, you will get a better clarity. Don't worry about it. Okay, think about it.
yes, sir, understood.
Understood? Okay. So just wanted to give an update. Sir, Math sir will join in 15 more minutes. So you can join at 5:15, guys. Okay. This session we can log off.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.